Greetings from Microlab Northwest. Today I thought we'd go into a little bit of the background, the physics that's involved in microscopy. Just a bit. I don't want to make this a class in physics, but it's nice to understand how light interacts with matter. In order to do that, we need to consider a couple of simple features. One of them is the fact that light can be modeled effectively as a wave. Now, one of the fascinating things about humans is that they are born in an environment that is full of waves. These waves are detected by basically two different senses. Our eyes detect what are called transverse waves. That's light. Our ears respond to pressure waves, sound. We learn about our environment by these waves that are constantly bombarding us. That is a key to how we sense our surroundings, everything around us. In the case of light, light is a transverse wave. What does a transverse wave mean? A wave has specific properties. Both transverse and pressure waves have specific properties that can be measured. If we were, for instance, to take a rope and attach it to an anchor, and then move that rope up and down, the rope doesn't move to the anchor, but the wave does. A transverse wave is a wave whose energy is up and down, not in the direction that the wave travels. If we look at a body of water and something floating on the surface, as the waves on that body of water pass the object moves up and down. It bobs up and down. It doesn't travel with the wave. Light is like that. The energy is at right angles to the propagation direction of the wave. So what are the properties of this wave? Well, when we look at a body of water and we see waves, the waves have a length. If we look at the crest of the wave, the distance to the next crest is a specific measure, a specific distance. That's called the wavelength. What's another property? How far is the object displaced that's sitting on the surface? That distance is referred to as the amplitude. Now, a wave has both a crest and a trough. Well, we draw a line between the two at the 50% mark, and our amplitude is the displacement from that surface. In other words, if there was no wave on the surface, that would be the level of the water. But because there is a wave, there is a displacement both above and below where the quiet body of water would have its surface. So we have amplitude and we have length there's another property, and that property is referred to as frequency. When we look at a traveling wave, we can speak in terms of how many wavelengths or how many crests pass us at a given unit of time. That unit of time and the number of crests tell us the frequency of the wave. In other words, how many wavelengths per unit time? That's a unit of measure. So we have these three characteristics of a transverse wave that give us information about the wave. Its amplitude, its wavelength, and its frequency. There are some other properties that we'll look at and consider in the future, but for right now, those are the properties that we're going to be considering. Now, when we look at objects in our environment, we are actually seeing differences in the properties that the wave is traveling through. You know, in the Middle Ages and before, they had thought of light as being a wave. Huygens in France, back in the 1600s, thought of light as a wave and actually demonstrated that it does in fact have properties that are identical to that of a wave. Prior to Huygens, an individual called Wilfred Snell discovered that if you had a tank and put a ruler at the bottom of the tank and looked through a sight, you could pick out a particular distance, a particular location that you were looking at. If you then filled this container with water and looked through the same sight, you no longer saw the same point. You saw something that was closer to you than it had appeared before. That was referred to as refraction. The light appears to be bent at the interface. After a number of experiments, Snell actually came up with an equation that allowed you to predict where you might observe that ruler, what measure you might come up with, depending upon the different substance that you had in this tank. Snell assigned a number to the material called the refractive index. The refractive index is a measure of the relative density of electrons in that material compared to another material. So the refractive index is actually a measure, basically, of the electron density. Snell didn't know that. Neither did Huygens, almost 80 years later. But today we know that that refractive index is really a measure of the electron density. One of the interesting things about matter, well, for that matter, about the universe, is that there's no such thing as an empty space. Where we don't seem to have much matter, we still have a force field. The force field that we're going to be considering is the electromagnetic force field, and it covers the entire universe. Light travels with this force field. It is a disruption, a traveling disturbance in the force, the electromagnetic force field. That's what allows it to travel from the sun to the earth. But using that same model, every single material modifies the electromagnetic force field in that specific area, that region, that specific region. So when a beam of light strikes something, it is in a different condition of the force field, and as a disturbance in the force field, it travels differently through every different material. We couldn't see anything if the electron clouds that make up an object were the same in everything. Everything would be invisible to us. What we are seeing is differences in the electron cloud density in each object. And each object treats that disturbance in the force field differently. It might reflect the disturbance. It might absorb the disturbance. It might transmit the disturbance. But it will always leave its mark on the disturbance, on the beam of light that's interacting with that surface. When we're using the light microscope, that's exactly what we're doing. We are looking at how something disturbs, how it modifies the disturbance that is the light beam as it travels through that material, or as it reflects off that material. Those are all indications of differences in this electromagnetic field that permeates everything. Might be getting a little deep. Let's call that a day for right now, and we'll come back and we'll look at some other properties of light and how it interacts with materials, how it interacts with the differences in this force field that permeates everything. So for now, see you next time. Bye-bye.